N is just the number of stories above the base. For us today, that's just 1, so N equals 1. Now we're back to the seismic importance factor, IE. So this can be found in table 1.5-2. So let's head over. Here we are at table 1.5-2. And what we have here are our importance factors, actually for everything, for snow, for ice, for seismic. So we're going to look through, and it just depends on our risk category. So our risk category, again, we know is 2, so it's here. And then we're not looking for snow, we're not looking for ice, or ice for wind. So we need just seismic. Seismic for 2, if we go all the way over, is just 1.0. Okay, fantastic. Let's jump back. IE 1.0. Now the next things we're going to need are as follows. R, omega, C sub D. Now R is your response modification coefficient. Omega is your system overstrength parameter. And C sub D is your deflection amplification factor. Boy, that seems like a mouthful. But these are all factors that apply to the type of structure that you are building to resist your seismic forces. So for us today, we are designing, and in the future we'll be designing a wood structure. So let's jump into the code knowing that, and let's try to find these factors. So here we are at Chapter 12 of the ASCE 716. This is Seismic Design Requirements for Building Structures. Now you need to be careful because there's multiple chapters moving forward where it has the same title, but it's for other things. So pay close attention to that because it covers all types of structures, not just building structures. You know, you have water towers, you have generators, you have, equipment. Those need to be seismically anchored as well. So, and there's many, many more things that fall into the category, but for us, we're designing a building structure. So we are at Chapter 12. We're going to scroll down, and what Chapter 12 has is Table 12.2-1, which is this really, really large table that consists of basically all building seismic force resisting systems for any type of structure. And where we're going to go is we're going to look through. We have bearing wall system because that is what a wood structure is comprised of. It's comprised of bearing walls and shear walls that hold up your structure. You know, you don't have wood structures, typical 2x wood structures aren't moment frame connections or anything like that, or any concrete, obviously, or anything of the sort, or any steel involved. So we are simply a bearing wall system. And then if we look down here, you'll see as we get lower, you have light frame wood, light frame cold form steel, light frame walls with shear panels of all other materials, light frame cold form steel, blah, blah, blah. So what really sounds like the winner to me, I'll erase these out, is number 15. Light frame wood walls sheathed with wood structural panels rated for shear resistance. Boom, that is us. So, and if you look above here, you have R, you have omega, and you have C sub D. So you have all of that criteria provided to you. You just need to know how to go find it. So we have 6.5 for R, 3 for omega, and 4 for C sub D. And now if you look even further over here, I'll get this out of the way, you'll see seismic design category. This gives you your limitations, your structural system limitations. So you can only do so much with a certain type of seismic resisting system. You can't have typical wood structures with sheathing as we specified in the location. Light frame wood walls with sheathing, that can't be the seismic force resisting system for a 100-story structure. It's just that's not allowed, not permitted. So if you look down here, we just need to make sure based on our design criteria. So seismic design category, is D. And if we come down, you'll see 65, which is including structural height limits. So that is the limit of our structure that we could construct using this type of seismic resisting system, is a structure that's 65 feet tall. Well, ours is only, 16 feet tall, so we're fine. We are permitted to do that. Okay. If you see NP, like right here, that means not permitted. So keep an eye on those. The code does kind of help you along to say, hey, you can't use that right off the bat. You need to design with some type of other seismic force resisting system, which is pretty great. All right, so let's jump back and get that info down. So R, we said, was 6.5. Omega, we said, was 3. And C sub D, we said, was 4. Next, we're going to jump back into Chapter 12 and start to move along with the seismic design criteria and what's still required. Now, if we look, I'm going to start us here in Section 12.6, Analysis Procedure Selection. Now, there are a couple different types of analysis procedures that you can use to analyze your structure under seismic loading criteria. And if we scroll down just a little further here, they provide a table for you. Permitted analytical procedures. So you have ELF, which is equivalent lateral force procedure. You have modal response spectrum analysis. And you have a nonlinear response history procedure. You can see this one's in Chapter 16. This modal response spectrum analysis, it's in Section 12 still. And then you have equivalent lateral force procedure, Section 12.8. Today we are going to be using ELF, equivalent lateral force procedure, so this guy right here. And that's pretty typical. If you start to get into some fancier structures with some pretty unique geometries and loading requirements, and in locations that are really, really close to fault lines or need to be designed for really demanding seismic criteria, then you most likely would get pushed into the next two analytical procedures. But for us today, we're just ELF. And if we look down, well, let's see, can we even do that? This code actually tells us. So for seismic design category, B, C, D, E, and F, all structures are permitted. Okay, well, that's great. That's pretty straightforward. You can use all three of them. Risk category 1 or 2 buildings not exceeding 2 stories above the base. Well, our risk category is 2, and we're not exceeding 2 stories above the base, so yes. And of course, we're permitted. So we're allowed. You basically, everything is permitted to use. But if you fall out of any of these criteria through here, if you like to read those all, we're not going to do it today, you would then fall under all other structures, and then you see here, you have the one non-permitted for equivalent lateral forces, which would then dump you into having to design with the 2 other analytical procedures. That's for a whole other day. So today, we know that we are designing with ELF. If we scroll down here, boom, Section 12.8. Equivalent lateral forces, ELF procedure. So this is where it all starts. This is where we're going to get our seismic base shear. That's what we're looking for, as well as some other criteria here. But that is the main force that we need in order to design our structure laterally. That is given just by the equation V C sub S W. W is the effective seismic weight per section 12.7.2. So we could jump over to there, but in today's example, we're going to give the weight of our structure. So let's jump back quick. So our effective seismic weight, we are going to say, is 128 kips. Now let's jump back over to code and see what else we need. We need CS, or C sub S, which is the seismic response coefficient determined in accordance with 12.8.1.1. Which is right below, obviously. So the seismic response coefficient CS shall be determined in accordance with equation 12.8-2. If we scroll up here, 12.8-2, this is your C sub S value. So it's SDS over R divided by your importance factor. And R, we know, is the response modification factor that we found from the large table based on our seismic force resisting system. So let's solve for that. So C sub S equals SDS over R over IE. STS is 0.64, R is 6.5, and I is 1.0. That's going to get us 0.098 as our C sub S. But we're not quite done there yet, so let's take a look back. So we need to make sure that we don't exceed the following. So for T less than or equal to TL, and for T greater than or equal to TL, well, what are those T's? So if we scroll down, T is the fundamental period of the structure, determined by 12.8.2, and TL is the long period, transition periods, determined in section 11.4.6. So first, let's find TL. So TL is actually in chapter 22. So if we go to figure 22-14, which I've jumped to here, this is a mapped long period transition T sub L. And if we look up here, so for everyone, long view is like, it's like right there. So we fall under T sub L, our long period of 16 seconds. All of these are seconds. So let's jump back. TL is 16 seconds, but we still need T. Well, if we jump a little further, we will go back to T, section 12.8.2. Let's see what they have in store for us. So 12.8.2, period determination. So the fundamental period of the structure T in the direction under considerations shall be established using the structural properties and deformational characteristics of the resisting elements in a properly substantiated analysis. The fundamental period T shall not exceed the product of the coefficient for upper limit on calculated period CU from table 12.8-1 and the approximate fundamental period TA, determined in accordance with section 12.8.2.1. Boy, that was a mouthful. Well, as an alternative to performing an analysis to determine the fundamental period T, it is permitted to use the approximate building period T sub A, calculated in accordance with section 12.8.2.1 directly. So that is what we're going to take advantage of. So this last portion here, T sub A. And T sub A, like they said in this section, can be found using this equation. So now we need CT, HN, and X. Well, if we scroll down a little further, those are provided in the following tables. So you have CT and X. If we scroll down, you'll see that it's based on structure type. And if we look through all of these, none of them match a wood-framed, light wood-frame structure. So that means we're going to fall under all other structural systems. So CT is 0.02 and X is 0.75. So let's jump back and write those down. So T, we're actually going to use TA, approximate. TA is equal to CT times HN raised to the X. CT is equal to 0.02. That's our approximate period parameter. Then we have X, which equals 0.75. That is also our approximate period parameter. It's the two parameters. And HN, we already know, is 16 feet. So if we plug all those in, we get TA equaling 0.16 seconds. And that's our approximate fundamental period. Now that we have TA, which is substituting T, we can now see that TA is less than or equal to TL, which means if we go back into the code, which equation do we get to use now? So we scroll back up, and now we find ourselves back in this neighborhood. Let's see here. So this is equations 12.8-3 and 12.8-4. We have T less than or equal to TL, which means we use this equation. So CS, because we want to make sure, again, what we're doing here is the value of CS computed with below not to exceed the following. So we found our CS before using this equation, but we want to make sure that it's not greater than the equation below here, that doesn't exceed that. So our C sub S max, we'll call it, equation is equal to SD1 over TA times R over IE, 0.538 over 0.16 times 6.5 over 1.0. That gets us 0.517, which is greater than C sub S equaling 0.098. So we're good. We know that C sub S does not exceed C sub S max. So we know that C sub S does not exceed C sub S max. So we know that we can use it. It's allowed. If we look back up above, all this was for finding our base shear, V. And V equals C sub S W, which is our effective seismic weight. Well, C sub S, we know now, and W, we know as 128 kips. So our seismic base shear is equal to 12.6 kips. And what that force is, so if we draw our structure again, that being the ground or the foundation, let's say that's the foundation. You know, you have your foundation here, and you have your roof. That is the force in shear that's acting at the top of your foundation of your structure due to seismic lateral forces. So that is 12.6 kips. Next, what we need to do is we need to find our vertical distribution of lateral forces. What we're going to need next is K, and what we're going to need next is K. N we know is 1 for number of stories. GE, which is actually our ground elevation. Ground elevation in this case, it's pretty much sea level, so we're going to say 0 feet. And that's pretty much, so K is pretty much the last coefficient that we're going to need to find. So let's go dive into the code that can be found there. So K is our exponent related to the structure's period, and that can be found in section 12.8.3. So let's get over there. All right, here we are, 12.8.3. If you look down below here, K, an exponent, like I said, related to the structure's period as follows. So for structures that have a period of 0.5 s or less, K equals 1. For structures that have a period of 2.5 s or more, K equals 2. And for structures that have a period between 0.5 and 2.5, K shall be 2 or shall be determined by linear interpolation between 1 and 2. So the value is based on the structure's period. Now we know TA is 0.16 seconds. So for structures that have a period of 0.5 seconds or less, which is us, K is going to equal 1. All right, so let's jump back. K equals 1. Done. Now, we need to distribute our base shear to our effective height. So like we talked about here before, this being HN, we need to know, well, how much of that base shear needs to be applied at that height for our lateral analysis. And actually what's really happening here, since we're just having a single story, what this would really equate to over time here is if you had a structure, say you had a high-rise or something, and you had multiple stories. So you can have your base shear down below, which you calculate, but then it comes down to a distribution of forces across each one of these floors. How much force is being applied at each one of the floors, and then once you have that, then you design your structure lateral system. But for us today, it might look pretty simple because it's just a single story, but that's where this upcoming table comes from.